Chaos theory module. System described. Chaotic system simulation. A logistic map simulator, an interactive simulation of the chaotic system described, demonstrating sensitivity to initial conditions, stabilization, and forecasting. An adaptive epsilon calculator, a tool to visualize how system and task parameters dynamically adjust the core epsilon stabilization value. AFC formulary, a comprehensive reference guide displaying the mathematical foundations and formulas from the document. LLM analysis results. Based on the provided system description, the primary form of circularity identified is the iterative nature of the logistic map itself. 1. Identified circularity, the logistic map iteration A. Description of the circular pattern asterisk the core of the system is defined by the equation xn plus 1 equals r asterisk xn asterisk 1 xn. This is a first-order recurrence relation. The value at step n plus 1, xn plus 1, is directly computed using the value from the previous step, xn. This creates a closed loop where the output of one step becomes the input for the next step in a continuous cycle. Starting from an initial value x, the process generates a sequence x, x2, x3, where each term feeds back into the generating function to produce the subsequent term. B. Potential implications and effects asterisk this iterative feedback loop is fundamental to the dynamics of the logistic map. Asterisk stability asterisk, depending on the value of the growth radar, the iteration can lead to different behaviors. For our values below 3, the system typically converges to a single stable fixed point. Asterisk oscillation / periodicity asterisk 4 are values between 3 and approximately 3.5699. The system exhibits period doubling bifurcations, settling into stable cycles of increasing length, period 2, 4, 8, etc. The given r equals 3.27 falls within this period doubling regime. Specifically, it is after the first bifurcation to period 2. Asterisk chaos asterisk 4 are values above the Feigenbaum constant, almost equals 3.5699. The dynamics become chaotic for most initial conditions, exhibiting sensitive dependence on initial conditions, aperiodicity, and fractal structure in the attractor. The mention of chaos theory module suggests the system is designed to handle or analyze these nonlinear dynamics. Asterisk sensitivity asterisk the feedback loop is the mechanism through which small initial differences are potentially amplified over time, leading to the sensitivity characteristic of chaotic systems. The sensitivity analysis mentioned likely measures this divergence, which is a direct consequence of the iterative feedback. Asterisk forecasting asterisk the iterative nature enables forecasting, predicting xn plus 1 from xn, as shown in the forecast output. This relies directly on the feedback rule. C. F0Z context asterisk in an F0Z framework. This iterative process represents the core dynamic system being observed, analyzed, and potentially influenced. Asterisk modeling asterisk the iterative equation xn plus 1 equals f xn itself is the model of the system's internal dynamics. The F0Z system models this process to understand its behavior: stable, oscillatory, chaotic. Asterisk observation asterisk the simulation output, the sequence of xn values, value at step 10, x, analysis, and forecast are all observations or derived analyses based on the output of this iterative loop. An F0Z system observes these outputs to gauge the state and behavior of the underlying process. Asterisk leveraging / control asterisk an F0Z system could potentially leverage this circularity. For example, asterisk by adjusting the parameter r or intermittently changing x_n, a form of control or perturbation, an F0Z agent could attempt to steer the system towards a desired dynamic state, e.g., stabilize it at a fixed point, encourage a specific oscillatory period, or maintain it within a chaotic but bounded region for optimal performance or robustness, aligning with the concept of finding a zero state, minimal effort for desired output.